Hello everyone, I'm Giulio and today I'm going to talk about tight verifiable delay function. This is a joint work with Nico, Döttling, Sanjam, Garg, and Prashant, Vasudevan. Verifiable delay functions, VDF in short, is a primitive which was recently introduced by Bonnet et al. In Crypto 2018, and it is essentially a function f that has two properties, sequentiality and verifiability. Sequentiality says that it takes roughly time t in order to evaluate f, and verifiability says that one can check whether a certain input x and a certain output y are in the relation f of x equal y in time much smaller than t. In particular, this means that verifying whether an input-output tuple is valid, it's much faster than actually recomputing the function itself. A little bit more formally, a VDF consists of three algorithms. The setup algorithm takes as input the security parameter and returns the public parameters, which are also taken as input by all other algorithms. The evaluation algorithm takes additionally as input an instance x and a time parameter t, and returns an output y together with a proof pi. The input-output pair xy together with the proof pi and the time parameter t are then taken as input by the verification algorithm, which returns either 0 or 1, meaning that the verification algorithm is convinced by the proof pi whether f of x equal y or not. As for efficiency of a VDF, we required that the algorithm satisfy the following bounds in terms of runtime. The setup algorithm should run in time polynomial in the security parameter, which in particular means that is independent of t. And the evaluation algorithm should run in time c times t for a certain constant c. Finally, the verification algorithm should run in time polynomial in lambda and logarithmic in t, which means that for a growing t, the runtime of the verification algorithm is much faster than the runtime of the evaluation algorithm. In this work and throughout this talk, we say that the verifiable delay function is tight if the time it takes to run the evaluation algorithm is very close to t, and in particular if the constant c is approximately equal to 1. I'm now going to give a more precise definition of the property that verifiable delay functions shall satisfy. So the first property that I'm going to talk about is sequentiality. Sequentiality says that for all parallel run algorithms A with depth at most t for some time parameter t, it holds that the distribution of the instances together with the output of the verifiable delay function over that particular instance is computationally close to uniform, where the instance x is uniformly sampled, and the time parameter and the public parameter of the verifiable delay function are sampled according to the setup algorithm. This in particular means that for a uniformly sampled instance x, the output of a verifiable delay function is unpredictable to all algorithms A which don't have enough time to actually compute the evaluation function. The second property that we consider is soundness, which says that for all probabilistic polynomial time algorithms A, it holds that the output of the algorithms A, which consists of an instance x, an output y, and a proof pi, cannot convince the verify algorithm to accept if x and y is not a valid input-output instance of the verifiable delay function, which again in particular means that an adversary is not able to fool the verification algorithm to accept a tuple xy such that f of x is not equal to y. Verifiable delay functions have gained a lot of momentum recently and have attracted a lot of attention both from the research community and from industry. And here I'm going to exemplify their utility with a very simple task that verifiable delay functions are very useful to solve. And the task is one of the most fundamental problems in cryptography, which is n mutually distrustful parties want to compute a certain coin, and we want to guarantee that such a coin is unbiased even if the majority of the parties might be corrupted and colluding towards biasing the output of the coin. To understand the main ideas of the algorithms, I'm going to first give a coin tossing protocol without using VDF, and I'm going to show why it fails to achieve the advertised properties. The protocol proceeds as follows. As a first step, each party locally samples some random coins Ri, and then it computes a commitment to such a coin, which it subsequently broadcasts to all other parties. Once all the commitments are received, each party outputs the opening of their commitment, which certifies that the random coins Ri were indeed contained in the commitment sent in step 2. At this point, once all the openings are received, we can set the output of the protocol to be the XOR of all the random coins sent by all parties in step 3. So the question that we ask now clearly is whether the resulting random coin R is truly unbiased. And unfortunately the answer is no. And in particular, consider the view of the last party that opens the commitment in phase 3. At that specific point in time, the party knows the opening of all the other parties, so in particular it can recompute the value of R, and it can decide to abort the execution of the protocol if he doesn't like such a value, and continue if he does like such a value, which in particular means that the distribution of R is not going to be uniform for a certain corrupted party. And note that if such a party decides to abort, there is no way for us to recover from such an abort because of the hiding property of the commitment scheme. And this is actually a more general instance of a problem, which is called fairness. And we actually know that fairness in cryptography is an impossible problem, typically, to guarantee fairness in such a protocol. So we are going to bypass this barrier by introducing some timing assumption, and in particular by assuming verifiable delay functions. So let's revisit our coin tossing protocol, this time using verifiable delay functions. Step 1 proceeds as before. Each party locally samples some random coins Ri, but this time it just broadcasts the random coins Ri in the plane to all other parties. And in step 3, the output of the protocol is set to be the evaluation of the verifiable delay function on input the time parameter t on the instance which is determined by the concatenation of all randomness of all parties that they send in step 2. And here t is a time parameter that determines the timeout of the protocol, which in particular means that all randomnesses received after time t are ignored and not considered to be part of this protocol. And again, the question that we ask is whether this protocol produces an unbiased coin to the eyes of a computationally bounded adversary. And the answer is yes, by the sequentiality of the verifiable delay function, because in particular, the adversary should not be able to predict the random coins sent by the honest party in step 2, which in particular means that is not able to predict the instance over which the verifiable delay function will be applied. And this means that by the sequentiality of the VDF, the output of the verifiable delay function on input that specific instance is computationally close to uniform. I'm now going to comment a bit on the state-of-the-art of verifiable delay functions construction, and in particular on what was known prior to our work. So the first construction that I'm going to talk about is verifiable delay function from succinct non-interactive argument, SNARKs in short. And it's actually not hard to see that given a SNARK, I can construct a verifiable delay function which is unconditionally secure in the random oracle model, and it has an optimal proof size, so constant size proof, again in the random oracle model. And the prover complexity is not optimal, in particular is some constant time, the time parameter t, because computing a SNARK over a certain sequential computation takes more time than the actual computation itself. An improved construction suggested by Bonnet et al. Builds on incremental verifiable computation, which achieves, again, constant size proof, but this time optimal prover complexity, which means that the proving algorithm runs in time exactly t. However, the price to pay for such an efficiency is the non-black box use of random oracle, in particular non-construction of verifiable or incremental verifiable computation built on the recursive composition of succinct non-interactive arguments. And at present is not known how to construct incremental verifiable computation, just making black box use of random oracle. This also means that in practice, construction based on incrementable verifiable computation are going to be typically much less efficient than construction based on plain snarks, due to the non-black box use of cryptographic material. More recently, two verifiable delay functions construction have been proposed, one by Christoph Petersak, the other by Benjamin Wesolowski, both based on the hardness of computing squares over a non-order group. And the assumption here is that there is essentially no much better algorithm than repeated squaring in order to compute 2 to the power of t power in groups of unknown order. And the two proposed construction achieve similar efficiency. In particular, Wesolowski's construction has proof size constant, is just one group element in the groups of unknown order, and the prover complexity is tight. However, it requires an additional assumption, which is the adaptive root assumption, needed in order to prove the soundness of the protocol. Whereas the construction of Petersak has a slightly larger proof size. In particular, the proof consists of log t elements, and the prover complexity is just square root of t. However, the soundness is unconditional in the random oracle model for the non-interactive variant, and just unconditional in the interactive variant. And the question that we ask in this work is whether we can improve the prover complexity of all these VDF constructions. In these settings, we obtain the following positive and negative results. So our first result is positive and says that if there exists a verifiable delay function with a runtime of the prover of c times the time parameter t for any constant c, then we can take this verifiable delay function and upgrade it to a verifiable delay function with a tight prover. On the negative side, we show that there exists no black box construction of a verifiable delay function in the random oracle model, where the prover makes at most t plus big O of t to the power of d queries for some d smaller than 1. And I shall mention that the same result follows also from a recent work of Mahmoudi, Smith, and Wu, appeared at ICALP 2020. Due to time constraint, for the sake of this talk, I'm just going to talk about the first result, but I encourage you to look at the paper in order to get an intuition and see also our negative result. In order to prove our first theorem, I'm going to refine the syntax of a verifiable delay function and introduce a property that we call self-composability. First of all, I'm going to split the evaluation of a verifiable delay function into two subroutines. The first subroutine, I call it compute, and the second subroutine, I call it prove. And computing just takes care of computing the function output y given an input x, whereas the prove subroutine just takes care of computing a proof pi given an input x. Finally, we say that the verifiable delay function is self-composable if the output of the computation algorithm on input a certain instance x and on time parameter t0 times t1 is equal to the output of the computation algorithms applied recursively, or first for time 0, then for times t1 over the same input x. This in particular means that applying the compute function over any intermediate step of the computation still leads to the same result. And while this is an additional assumption on the structure of the VDF, I should mention that such a property is satisfied by all instances of VDF known thus far. So I'm now going to give an intuition on how to take a self-composable VDF, which is non-tight, and how to construct, starting from this, a VDF which is tight. And for the sake of this talk, I'm just going to consider some simplified settings, where the compute algorithm takes as input exactly t, but the prove algorithm takes as input takes time 2 times t, which in particular means that the total runtime of the VDF is 2 times t, so that the input VDF is not tight. And the basic idea of our compiler is very natural. First, I'm going to take the evaluation of a VDF with time parameter t over 2 and run both the compute algorithm and the prove algorithms in parallel. Note that the prove algorithm will terminate at time exactly t, whereas the comp algorithm will terminate much earlier. However, is going to output some intermediate value of the computation, which is not the actual output of the verifiable delay function. However, at time t over 2, I'm going to spawn a parallel processor which is going to compute the verifiable delay function on input, the intermediate value y0. And at the same time, I'm going to prove that the corresponding computation is well formed. And note again that by setting the parameters correctly, my proving algorithm will terminate exactly at time t, whereas my compute algorithm will terminate at 3/4 of the t. Note that y1 is again not the correct output of the verifiable delay function, but it's instead an intermediate value of the computation, but you can see that we are approaching closer and closer to the actual output of the verifiable delay function. So we can repeat this procedure recursively over and over until the compute algorithm has to do only a constant amount of steps. And at that point in time, there is no need to produce a proof for that, because the verifier can just recompute those steps himself. Now, the proof pi of our tight verifiable delay function consists of all the intermediate value of the computation that I computed, together with the corresponding proof of well-formedness. And it is not hard to see that the resulting VDF is actually tight, meaning that the prover runtime is exactly t plus a constant number of steps. And this comes an increase of the proof size and prover parallelism by a factor of at most log t. So what happens when we take this compiler and we apply it to existing construction of VDFs? First of all, we obtain a tight VDF for the snark settings, and in particular, the compute algorithm is just repeated hashing, and the prove algorithm is just a succinct non-interactive argument that such a computation was well formed. So we take this construction and we lift it to the tight prover settings, which means that the runtime of the prover is approximately t. On the other side of the spectrum, we can take our compiler and apply it to the verifiable delay function of Peterzak and lift it to a tight regime, obtaining therefore a tight verifiable delay function just from the sequential squaring assumption, which has statistical soundness in a random oracle model. So to wrap up, in this work we have seen a bootstrapping theorem for a tight verifiable delay function, which allowed us to obtain new constructions of verifiable delay function with optimal prover complexity, and a lower bound for tight black box construction of verifiable delay functions in the random oracle model. And I'd like to conclude this talk with a few of my favorite open problems. So the first natural open problem is whether we can find efficient construction of verifiable delay function in the post-quantum settings, in particular the construction of Peterzak and Wesolowski, which are by far the most efficient instantiation of VDFs that we know, are known to be broken in the presence of a universal quantum computer. So the natural question is whether we can construct a verifiable delay function that withstands also the presence of such a quantum computer. Another very fascinating open problem is whether we can construct a verifiable delay function in the standard model without making use of the Fiat-Shamir heuristic. And there is some progress in that direction, but current constructions are very inefficient and are based on very strong assumptions. So it would be very interesting if we can lift such a construction to VDF in the standard model against well-studied and well-founded assumptions. So that concludes my video. I would like to thank everybody for their attention and to make it that far. Thanks everyone.